at ESF. Today, I am going to discuss about our project, which focuses on the efficiency of electron beam irradiation in removing emerging contaminants from the wastewater. The PIs of the project are Dr. Mark Driscoll and Dr. Alex Ardukin. And here is the outline of my presentation. I will briefly mention about the problem, as well as giving a short background about the problem. And I will also be giving the objectives of the project, following by the flow chart of the analysis. And lastly, I will talk about the results and conclude the The background is a picture of Onondaga Lake, where we launched the boat to reach the metro wastewater treatment plant's outlet, to where we grab our wastewater samples. Okay. Densely populated areas and industrial cities primarily rely on centralized wastewater treatment plants, receive and treat sewage. Here is an illustration of a wastewater treatment plant. So we know that wastewater treatment consists of physical, biological, and chemical treatment steps. And once the wastewater comes into the treatment plant, screening, grinding, and separating large solids and debris from the wastewater takes place in the first stage in the wastewater treatment, which is also known as the preliminary treatment. In this stage, 6 large food particles, sand, even toys that are flushed down the drain must be removed from the wastewater to protect the pumps and the other wastewater treatment equipment. So next step is the primary treatment. In tanks for several hours to allowing heavy particles to sink to the bottom and grease to float to the top. And in the secondary treatment, which is also known as the biological treatment of wastewater, by using microorganisms to purify water and killing. The next step is the purpose of the final treatment is to kill disease-causing organisms, which is the last stage of the wastewater treatment. In this stage, chlorine is mostly used as disinfectant to kill disease-causing organisms, but because the chlorine is toxic, it must be neutralized before to the body of water. UV is ultraviolet light is another disinfection treatment, which is also done in the wastewater treatment plant. In our case, the wastewater is released into Onondaga Lake by the Syracuse Metro Wastewater Treatment Plant. Here is a problem. So even after treatment at wastewater facilities, we know that some chemicals, including pesticides, pharmaceuticals, plasticizer, and surfactants can end up in the effluent, which is discharged into rivers and flows into other water bodies. Therefore, in order to reduce risks to humans and the environment in a cost-efficient manner, additional treatment might be beneficial before releasing the effluent. Okay, so electron beam wastewater treatment plants are now being used commercially around the world. For example, we know that in Republic of Korea, a plant using electron beams at a relatively low doses in combination with biological treatment for wastewater. And also China has also set their first medical wastewater treatment facility with electron beam technology. Okay, so what does electron beam? In this method, high energy electrons react with water molecules and lead to the hydrolysis of water, radiolysis of water, resulting in the formation of highly reactive species, intermediate species, which are hydrated electrons, OH free radicals, and hydrogen atoms. So these intermediates are capable of breaking down most organic molecules. They provide partial or complete decomposition of organic pollutants, as well as removal of color and odor. Okay, so in the image which is shown in the right, it's an schematic view of electron beam accelerator in the wastewater treatment plants. The E-beam originates from a heated filament, which is under high voltage from the power supply. It is focused and accelerated within an evacuated acceleration tube, reaching an energy corresponding to the output voltage of the power supply. In the accelerator, the electron beam passes the anode through a hole, and it enters into a vacuum chamber where it is scanned by a varying magnetic field. Then the scan beam passes through a thin window to meet the water being processed. So the energy transferred from radiation to the matter, to the substrate, is described as the radiation dose, and the unit of radiation dose is known as described as gray. For water, 1 gray is defined as the absorption of 1 joule of radiation energy per liter of water. Okay, so radiation dose is the only parameter which is important to control the irradiation process, actually, and it is determined by the current, the beam current, and the water flow rate, which comes from here. And both parameters can be used to adjust the desired radiation dose for the treatment, for electron beam treatment. Therefore, the process is extremely simple, and the automation for this method, for this treatment method, is very easy to perform. Okay, so here are the objectives of our project. The objectives are to degrade any organic pollutant in wastewater without focusing on their identifications, and to assess the efficiency of electron beam depending on irradiation doses. The first picture shows the map of city of Syracuse, and Onondaga Lake is located in the central New York along the edge of the city Syracuse. Unfortunately, Onondaga Lake is the most polluted lake in the United States, and it's not only one of the most polluted lakes in the country, actually, but also ranks among the most polluted lakes in the world. The third picture belongs to the outlet of Metro wastewater treatment plant, where we went and grabbed our samples. So we know that the Metro wastewater treatment plant treats an average of 84 million gallons wastewater per day, which is a lot. So as for the flow chart for our analysis, we went by the outlet of the Metro wastewater treatment plant and collected our wastewater samples. And once we get back to the lab, we allocated these wastewater samples into 20 milliliter vials, and we send our samples to NYSDEC so that they treat our samples with electron beam irradiation at varying different doses. And the irradiated samples were then analyzed using untargeted high resolution LCMS method. And after that, we perform feature extraction and the comparative analysis by using MZMine software. Okay, so here are the results part. Our results show that there was an increasing degradation trend with the increasing irradiation doses. Table 1 shows the degradation trend for our first batch sample, and they were on June. The irradiation doses were 0.1, 0.5, 2, 5, 15, and 25 kilogray. And at 0.5 kilogray dose, almost 72% of the pollutants, of the organic pollutants, were degraded, and it has reached to 92% at 2 kilogray irradiation dose. So after getting these results, we also collected another wastewater samples in October and wanted to check the degradation percentage for the interval doses, such as 0.05, 0.2, and 1 kilogray, by keeping 2 doses as a control dose with the previous batch, which was 0.1 and 0.5. And we also increased the highest dose to 50 to check if any changes in the irradiation percentage. However, the results show that there were some differences at the control doses. Looking at the second table, we show that at 0.5 kilogray dose, we get 25% of degradation, 25% degradation of the organic pollutants, whereas we get 84% for the 0.5 kilogray, which were different than the first batch. Here you can also show the graphs that showing the degradation percentage versus doses, like different doses. And here you can see very steep, in this part you can see the graph is very steep, but this is just because we added 50 kilogray as the highest dose. So yeah, there were some differences in the degradation percentage for both batches. Okay, these two heat maps show the colorful degradation profile of two batches, depending on the irradiation doses. We got more than 10,000 features, in other words, more than 10,000 compounds in the wastewater for both analyses. And the first column of the tables represents the results for non-irradiated samples. So this one is the results that we get on June, whereas this shows the results for the samples that we irradiated on October. But just I would like to mention that we added some interval doses, which was 0.05, 0.2. So therefore, there might be very different than the previous colorful degradation profile. And So as I said, the first column of the tables represents the non-irradiated samples, and the rest of results for the irradiated doses have been normalized by the non-irradiated results. I mean, like we normalize these results with the non-irradiated one to see the comparison between non-irradiated and irradiated ones. Okay, so here this bar shows a transition from green to red color. The green color shows that the pollutant exists in the sample, as you can see in the first columns. And then the red color shows that the amount of pollutant has decreased or it does not exist anymore in the wastewater. All right, so this is a TIC chromatogram, which shows the total ion in the sample. This chromatogram created by summing up intensities of all mass spectral mass peaks belonging to the same scan, and the black peak stands for the non-irradiated sample. It has the highest amount of ions. That's why it has the most the highest area under the peak comparison to the other peaks, which are shown by red, green, purple, and pink. And we understand from this chromatogram, we understand that with the increasing irradiation dose, the total area under the peaks are decreasing. That shows us as the irradiation dose increases, the degradation also increases. So gray color, I'm not sure if you're able to see this peak. This also represents DI water, and it has the least amount of ions, which shows us it has the less amount of total ions. Okay, so here is another table showing the degradation of non-organic pollutants at different electron beam irradiation doses for the samples that we treated on June. And we extract from our whole list, as I said, it has more than 10,000 compounds inside. So we just extracted some of non-pollutants that we have on our list, such as rubber additive, plasticizer, and most of pharmaceuticals. Their degradation profile by the different doses. So most of them have a tendency to completely degrade as the irradiation dose increases. You can see it just turns to red. However, we were not able to degrade PFAS compounds, which exists in the beginning of the process, and even after 25 kilogram irradiation, it still exists in the wastewater because it requires more energy to break down. So we know that perfluorinated compounds are not does not degrade by this method. So as for the conclusion of the project, we were able to degrade organic contaminants with an increasing amount of electron beam. And as I showed, there were some differences in the degradation profile, which we believe that most comes from the different amounts of dissolved organic matter in the two batch. Because like we collected first batch in July, whereas we collected the second batch on October. And Another conclusion is, as I showed in the previous slides, we were not able to degrade perfluorinated compounds under low doses of electron beam irradiation. And another thing is we know that electron beam is cost effective and it's a very efficient way to degrade pollutants in a very short period of time, because it takes almost a second. In the future, we are thinking to do additional experiment on this project by adding various amount of dissolved organic matter to the wastewater samples and see if dissolved organic matter really affects the degradation efficiency. Okay, so I would like to special thank to Dr. Driscoll, who is my advisor, and to Dr. Alex Artyukin to give me an opportunity to be a part of this project. And we would like to thank to New York State Wastewater Resources Institute for their support. Also, I want to acknowledge the contribution of National Institute of Standards and Technology for offering their radiation facility for the irradiation of samples in support of this project. Okay, I'm gonna stop sharing my screen.
Yeah, great job. Thank you.
And I'll take over now for you, Dilara. So hi, everyone. Thanks for having me on to speak today. My name is Ryan Elliott, and I'm the Western Great Lakes Watershed Coordinator for the New York State Department of Environmental Conservation's Great Lakes Program. I'm going to discuss why we were interested in supporting Dilara's work and some potential applications of the electron beam radiation treatment. So first, I'll discuss what interest there was in the project and briefly touch on some connections to plans that guide Great Lakes management. Dilara's work was of interest to stakeholders at various scales, all the way from the federal government down to local interests. The project proposal received 6 layers of support, including the National Institute of Standards and Technology, DEC Region 7 Regional Director, New York Power Authority, City of Syracuse Engineering Department, and 2 private companies, Ramble and IBA. And this research is also relevant to numerous federal and state documents that guide Great Lakes management. One federal plan that is connected to Dilara's research is the Great Lakes Restoration Initiative Action Plan 3. The Great Lakes Restoration Initiative, or GLRI, is a non-regulatory federal program that was launched in 2010 to advance efforts to protect and restore the Great Lakes and to provide additional resources to address important long-term goals for the largest system of freshwater or fresh surface water in the world. In the GLRI action plans, this is the 3rd iteration, the 4th one is currently being worked on, outlines steps to achieve long-term goals for the Great Lakes and commitments under the Great Lakes Water Quality Agreement, which is a binational agreement between the US and Canada, which drives binational Great Lakes management efforts. And this GLRI Action Plan 3 has 5 focus areas. The first of these, toxic substances and areas of concern, is most closely related to Dilara's work. And for anyone who's interested in learning more about this document or any other documents I'll mention, I'll provide a list of links in the chat at the end of my presentation. And so at the state level, the DEC's Great Lakes program, where I work within DEC, drives work within the Great Lakes Basin in our state. The Great Lakes program was developed under the authority of the 2006 Ocean and Great Lakes Ecosystem Conservation Act, and the mission of our program that you see on the screen here is to protect, restore, conserve, and enhance the chemical, physical, and biological integrity of the waters and associated natural resources within the Great Lakes Basin for sustainable use and enjoyment by the people of New York. And the New York's Great Lakes Action Agenda is the document that guides the work of the Great Lakes Program and Great Lakes management efforts within New York State. And the current agenda has 10 goals, and the first 2, which are circled on the screen here, virtually eliminating discharges of persistent toxic substances and controlling sediment, nutrient, and pathogen loadings, are closely connected to Dilara's research, since electron beams can degrade a range of organic contaminants and disinfect wastewater. And be remiss if I didn't mention that the Great Lakes Action Agenda is currently being updated and that the new version should be released sometime this spring. The updated agenda integrates existing plans, priorities, challenges, and lessons learned from decades of previous work on the Great Lakes into a single plan for all of New York State. It emphasizes ecosystem-based management, which is an approach that strives to take a science-based collaborative approach to addressing ecological, economic, and social challenges and opportunities. And lastly, the Water Resources Institute was interested in supporting this work because it aligned with research priorities we have related to water quality, specifically work related to micropollutants and emerging contaminants. So now I'll discuss some potential applications for the electron beam irradiation treatment. And the first one of those potential applications I'm going to discuss is the use of electron beam irradiation at different types of wastewater treatment facilities. Publicly owned treatment works or POTWs like the Syracuse Metro plant that Dilara talked about, industrial wastewater treatment plants like chemical manufacturing plants, and on-site remediation projects. So Dilara's work has shown that electron beam treatment can effectively degrade a multitude of organic contaminants. However, these compounds are not typically the target of publicly owned treatment work discharge permits. In addition to the degradation Dilara described, this type of treatment can also disinfect wastewater. And one study by Maruthi et al. Showed that low doses of electron beam treatment within the range of dosages used in Dilara's study were effective at reducing total bacteria counts, total coliforms, and total Salmonella Shigella counts in wastewater. And many wastewater treatment facilities in New York, whether due to surface water quality standards or state pollutant discharge elimination system permit requirements, must disinfect their effluent prior to discharging it to a surface water body. When these facilities need to install or replace disinfection treatment technology, which is typically done using chlorination, ozonation, or UV disinfection, or ultraviolet disinfection, they could consider electron beam treatment as an alternative that would provide an additional benefit of degrading hundreds to thousands of organic compounds. And permits issued for publicly owned treatment works do not typically have limits for many of these organic contaminants, but they are more common in industrial wastewater treatment facility permit requirements. So this technology could also be used at these industrial facilities to meet their permit limits. And this technology could also be applied in the field at remediation sites. For instance, some sites require contaminated groundwater to be extracted, and in some cases, this water must be transported to an off-site facility for treatment. If an electron beam were brought into the field, it could be used to treat organic contaminants on site, eliminating or reducing the cost of off-site treatment. Proper shielding of the beam would be required for safe operation, which I will touch on more in a few slides. So the next potential application I'll talk about is the use of electron beam irradiation to improve drinking water quality. And so in addition to the wastewater treatment applications, which were the focus of Dilara's work, electron beams can be used to treat drinking water for compounds associated with harmful algal blooms. And for those of you who may not be familiar, harmful algal blooms, or HABs, shown in the picture on this slide, occur when colonies of algae grow out of control and produce toxic or harmful effects on people, fish, shellfish, marine mammals, and birds. HABs are a concern not only in our oceans and Great Lakes, but also inland water bodies, particularly those used for drinking water supplies, like some of our Finger Lakes. And harmful algal blooms can be associated with compounds that impact the taste and odor of water, as well as toxins that can negatively impact humans, pets, and wildlife. The compounds methylisoborneol, or MIB, and geosmin are associated with taste and odor issues. Microcystin LR is a toxin produced by Microcystis and other toxic cyanobacteria that can have damaging human and animal health impacts. So much so that it has also been referred to as fast death factor, which is a pretty horrifying name for a compound. And previous work by Dr. Driscoll, one of the PIs for Dilara's project, showed that a dose of less than 0.1 kilograde degraded all MIB and geosmin in a water sample, with no degradation products detected using gas chromatography with tandem mass spectrometry with solid phase microextraction. And a dose of less than 0.5 kilograde degraded all the microcystin LR, and there was only a noticeable degradation product detected at 0.1 kilograys using ultra high performance liquid chromatography with tandem mass spectrometry. And to wrap things up, I just want to touch on a few potential barriers to implementing this treatment technology. And the first of these is upfront funding. The initial cost for one of these electron beams is around $1 million, which is a price tag that will likely be too high for many municipalities to afford upfront. However, in cases where a permittee needs to disinfect effluent and/or address one or many organic contaminants as a permit or remediation requirement, this technology has the potential to become more cost-effective. If the technology would be comparable in price to a targeted treatment method that only addressed one of the organic contaminants in a permit, then this technology could be the preferable choice because it would degrade the contaminants included in the permit, disinfect effluent, and would degrade a multitude of other organic pollutants that could be present in plant effluent. Second potential barrier here is public perception. And radiation is a term that can send up red flags amongst the general public. And so a key to implementing any radiation-based treatment technology be to keep the public well informed of what risks are present when this technology is used and what measures are taken to prevent exposure. So to get into that a little bit, electron beam radiation produces beta radiation and X-rays, which require shielding to limit exposure to nearby workers. Beta radiation can be shielded by something as simple as a thin sheet of aluminum, whereas X-rays require more advanced shielding. And to limit exposure from electron beams, the beams are self-shielded or wrapped in high-density metal to contain radiation. They have safety features to prevent opening the casing during operation, and small openings engineered with multiple angles to attenuate X-rays until they reach a background level. And additionally, electron beams use electricity rather than a radioactive source to generate radiation, so there's no radiation emitted when the beam is turned off. And as I mentioned before, proper shielding is always important, and it would be especially important if this technology were to be used in the field outside of an enclosed facility. Another potential, not so much barrier, but potential consideration would be the influent water quality that's coming into a treatment plant. And as Dilara mentioned, her study showed that there was preliminary evidence showing there are differences in the effectiveness of the electron beam irradiation treatment method, depending on the concentration of dissolved organic matter in the effluent. And further work is needed, as she mentioned, but if dissolved organic matter does indeed reduce the effectiveness of this technology, it may be less suitable for treatment systems whose influent contains a high concentration of dissolved organic matter. And the need for something like this type of treatment should also be considered in light of what sources are contributing influent to a treatment facility. For instance, in the case of the Syracuse Metro plant, there are 5 hospitals in the service area, so plant operators should expect a greater degree of pharmaceutical contamination, as opposed to a treatment plant located in a rural watershed without a hospital in the service area. And the last potential barrier to implementation would be permitting. And New York State regulates discharges to surface waters through the State Pollutant Discharge Elimination System, or SPEDIES. And the DEC reviews treatment system designs against 10 state standards and TR 16, both of which guidance documents include provisions for new or alternative technologies. And the 10 state standards include language that states the policy of the reviewing authorities to encourage rather than obstruct the development of any methods or equipment for the treatment of wastewater. So it is typically the case that a permittee will be responsible for proposing and installing technology that they can demonstrate has the ability to achieve the desired level of treatment, rather than the state specifying a specific technology to meet permit limits. And that wraps things up for me. I have all my contact information on the slide here. And as I mentioned, as soon as I stop sharing my slide, I'll grab all the links for various documents and programs that I mentioned so that people can dig into those resources as they have time to. Thank you very much.
Thanks, Ryan and Dilara. If people have questions, please feel free to just unmute yourselves and ask. You can also leave questions in the chat and I can read them out for you. So I guess I'll just give everybody a minute to ask questions.
I have a question. Thanks, Dilara. I was wondering, did you guys run, you have that big table of all the different compounds, many of which are, maybe like micropollutants or emerging contaminants, not typically regulated, many to most of them. Did you put together a table that shows only what it would do for regulated compounds? And in particular, right, I'd be curious as to whether you could meet permit guidelines. Although this is already effluent, so presumably it already does meet the guidelines for these particular samples, but just curious about that.
So we didn't put all the known pollutants together. We just we had some list of non-pollutants, so that's why we just extracted from the whole list to see the non-pollutants, and we just went there and then grab our wastewater. So we didn't get any permit for this.
Okay. Yeah, thank you.
No problem.
I see a question in the chat from Daniel. Do suspended solids impact the effectiveness of the electron beam to break down dissolved compounds?
Well, it might affect, but we were very carefully grab our wastewater, and it was no suspended solids. So, I mean, like, we didn't. It was clear. It was almost clear, but I think it affects the effectiveness of E-beam.
Mark, did you have a question or something to add to that? I saw you unmute yourself.
Yeah, I unmuted. This is Mark Driscoll, I'm Dilora's professor. So with the suspended solids thing, if it's organic, obviously hydroxyl radicals will attack any organic matter. So the more organic matter you have in there, the less efficient it is to go after one specific thing. If it's inorganic, unlike ultraviolet light, where things can absorb the radiation, color can do it. What stops the electron beam is just pure density. So if you have very dense particles, it can have some effect on how far the electron beam penetrates through the water column. But odds are against that at an effluent side, that you're going to have any significant amount of very heavy metals, dense metals in your system.
When you guys look at something like disinfection, like do you see it disinfecting again all the way down to like the types of levels that a treatment plant would be required to reach? Just thinking about like the feasibility of a facility replacing a current technology, or are we talking about adding a new technology?
So electron beam is, or radiation gamma ray 2, 25 kilogray is considered sterilized by the Food and Drug Administration. So if you hit 25, that water is considered sterile. So you can bag it up and use it as sterile water. Now you don't need that kind of kill, because I think that's 6 log kill for sterilization. But for disinfecting, it's much less. So I'm thinking roughly, I'd say 15 kilogray should give you disinfectant level. But if you could go out to 25, you know, FDA says it's sterile.
Thank you.
I see another question in the chat. Are there any concerns about new compounds formed after degradation?
So the compounds that are formed after degradation was mostly the small fragments. I mean, which were the broken down fragments. So we assume that there were no concern. The only thing, so we didn't see very how do I say? We did not see very high amount of organic contaminants, which does not exist in the beginning of the process, but then exist in the last part, exist at the beginning of the process. So therefore, I would say that there were no concern about the compounds after e-beam treatments.
That's always something you have to be concerned about. But one of the things I like to say to people is no one's running around after biological degradation trying to figure out what the really bad stuff is in there. All you're doing is partially degrading something, and the bacteria are doing the same thing. So yes, you'd have to be careful about it, but you just have to do some testing on the water itself to see if it's showing up toxic, initially with some small organisms, just to see if you're causing any problems, but we doubt it.
I have a question. This is Seth. Thank you both for your presentation. And Ryan, thank you for giving us some sort of point of reference on the cost. I was wondering if you could give us like a rough idea of how much other, like for example, UV treatment comparable systems would cost for a municipality.
I'd have to double check what the capital cost for a UV treatment system is. I remember seeing there were several awards for UV disinfection systems awarded through the Water Quality Improvement Project grant program this past year. So I could follow up with an answer for you and pull out some of the project costs that were in the last round of grant announcements, because that would probably be the most current range of estimates we have for New York State.
Thanks, Ryan.
Yep.
I had a follow-up question to that. Ryan, you did a great job of sort of summarizing the barriers that communities may face when they try to implement this. And you mentioned that there were some ways to get over the initial costs of installing an electron beam or integrating this into an existing wastewater treatment. Can you elaborate on what the cost reduction looks like and like what are the ways to reduce the cost? I know you went over it really quickly, but I was wondering if you could give it some more time.
It was less a reduction in the upfront cost of the beam and more so that if, as we mentioned, a lot of these organic contaminants aren't in permit limits, especially like the publicly owned treatment work permits. But if a facility needed to replace their disinfection technology and they had like an organic contaminant or two, all the co-benefits add additional, like it makes it more cost effective to treat more things, but without it being in the permit, it's hard for municipalities to justify that upfront cost. But in instances where this treatment would be comparable in cost to whatever individual treatments you would need to install to address organic contaminants or UV disinfection, it could become more cost effective as you if this was comparable in cost to multiple other treatment methods that would need to be installed to meet the same permit limits.
Thank you. That was helpful.
And if I could
No
just follow up on why we looked at this was, remember, today the big emerging contaminant of concern is what? PFASs. And they started being commercially produced in the late 40s, early 50s. And we're just worrying about them now. So if there's something that's being produced now that's going to be a problem 50, 60 years from now, we may be attacking it up front. And I know Ryan and I have had this long discussion about this. It's very difficult to get this implemented without any kind of permitting requirements. But this was our goal. And if you want to take it even further, we talked about the microcystin. Those blue-green algae or cyanobacteria, they've been around for 2 billion years. And now we're just starting to worry about them over the last 20 years. So these emerging contaminants, once we know about them, it's usually too late. We didn't get them when we should have, which was early on.
Hi, this question is probably for Ryan and Dilara. I was wondering what kind of operation and maintenance it takes for this treatment equipment, and if that is something that operators would need to be, trained on, and if that is a barrier at all to getting more implementation of this type of technology.
So, hey, Emily, so I think that you make a good point about training being a potential barrier here. I'm not as familiar with the inner workings of what it would take to operate and maintain one of the electron beams, and perhaps Dilara or Mark can comment a bit on that. But I do think that adding this into like developing wastewater operator training, if this technology was adopted as a way to get a local municipality staff up to speed on how to implement and operate and maintain one of these systems, would definitely be something that would have to be addressed if we want to see this technology implemented in a widespread manner.
Yeah, electron beams are widely used in industry, but we just don't know about it. So I assume everybody came to work today somehow using a tire, either by bus or by car. All those tires were pre-gelled with electron beam. You open up the hood of your car, all those plastic components cross-link with electron beam. And if you fly, all the wires and cables, the insulation is all cross-linked with electron beam. So there's this company called Raychem out in California. They run their electron beam 24 hours a day, 7 days a week for 6 months. They shut down to replace the window and the source and then start up again. They can run longer, but they have to stop and do maintenance on the rest of their line. So they figure they might as well do it while they're already shut down to do it on their electron beam. So from that, they should be able to run continuously for at least 6 months before any maintenance needs to be done on them.
Thank you.
Do we have any questions in the room? Okay, any more questions from anyone on Zoom?
Hello, I have a question. My name is Erin Norris. I was just curious, is there any sort of mechanism at the state level or regional level to track things like this? So that, as Mark mentioned, when emerging contaminants come out, it's typically it's later, and then you're kind of being reactionary. But is there a mechanism at the state where they can track, research like this so that they can stay in advance of, new items coming out or just treatment technologies? I know working in oil spill response, there's a schedule for understanding, basically chemical reactors, like with the National Contingency Plan Subpart J that the EPA and NOAA oversee. So I wasn't sure if there's anything at the state that kind of tracks these technologies for implementation later on.
Oh, hi, Aaron. I'm not familiar with any formal research tracking system that we have for the state, but we support research through the WRI grants, and we obviously keep a handle on all of that, and also through the Great Lakes Research Consortium. So any research that goes on through there, we should, the Great Lakes program does stay aware of research and new technologies, but don't have a formal way for advancing the technologies through the state. I can check with our Division of Water staff to see if they have any formal programs for addressing for identifying what the new contaminants are and new technologies for treating them. And I could, if you drop your email in the chat, I'd be happy to follow up with you on that.
Thanks.
Aaron, I was just looking at the DEC's HABS program guide this morning. And, for example, it does mention mitigating, technologies and things like that. This is like for HABS and open water and stuff. So it's not quite the same. You wouldn't apply the electron beam to like Cayuga Lake, but and they mention things like, ultrasonic technologies and what that does. So I think there's some stuff in there, but I don't know whether the New York Water Environment Association is sort of a like professional groups. I'm sure if you go to some of those meetings and you go out to the vendor display areas, people are aware of what technologies are coming out. So maybe no formalized document, but there are venues to talk about this stuff.
Thank you.
Thank you, Brian.
Okay, any last questions? Okay, great. I think we can wrap it up. Thank you so much, everyone, for coming. Thanks, Dilara and Ryan, for presenting. And we'll see you at the same time next week for the last session in our speaker series. Thank you so much, everyone, for joining.
Thanks for having us, Raywa.
Thanks, Dilara. Thanks, Mark.
Have a good day.